that we've got a region of space here, and in this region of space, we've got a magnetic field directed into the screen. Let's say the magnetic field has a magnitude of 0.0129 Tesla. And I'm going to shoot a beam of sodium ions in here. So my sodium ions, so they're single ionized sodium atoms. Okay, so that means one electron's ripped away. Remember, sodium has that just one outermost electron, is easy to pull away, leaves it as a positive sodium ion. And as it goes through here, it's going to pass between these metal plates right here. And the metal plates have an electric field directed downwards here. And the electric field here, I'm going to say the electric field has a strength of 19.2 volts per meter. Okay, so the sodium ions that are going too slow, the magnetic field, see, we got two forces acting on the sodium atoms. So the magnetic force is right-hand rule, V cross R. The right-hand rule says the magnetic force is going to be up, but the electric force is going to be down. So the magnetic force, we know the magnetic force, so the magnetic force, this is the force up, is going to be equal to QVB. The electric force, that's the force down, is going to be QE. So, if they're going too slow, the electric force is too big and they spiral downwards and they hit the plate. If they're going too fast, the magnetic force is too big and they spiral up and they hit the plate. If they're going just right, they go shooting out at all the same speed. And then once they get out, only the magnetic force works, and the right-hand rule says it goes this way. And so what will happen is it'll spiral around this way, and what I can do is put a whole bunch of detectors out here, and I want to know which detector does it hit. In other words, what is that distance right there that it goes? Okay, so I want to know what distance does it go and which detector does it hit. Okay, so first step is we got to find out what speed it's going. Okay, because I know that once it's outside of these metal plates, this is just cyclotron motion, and I know that the cyclotron radius is going to be mv over qb. Okay, so I need to know v. Well, I need to know m also. Okay, so there's several things I need to know but first of all, I need to know the v. Well, this is the velocity selector that we talked about earlier. So QVB is going to be equal to QE. So V is going to be equal to E over B. So that would be equal to the 19.2 volt per meter divided by the 0.0129 Tesla. Okay, now we got this whole confusing thing with units again. So this little v, now again, this, don't be confused. This is voltage. The other v down here is velocity. This is 1490. Now units. The units are a volt per meter Tesla. Okay, so how do we reconcile that before? Okay, so this becomes this confusing sort of mess that we had before. Okay, so one way of doing it is think about volt is a joule per coulomb. So a joule per coulomb, so a volt per meter Tesla. So a joule per coulomb is going to be a Newton times a meter per Coulomb meter, and then a Tesla, we said, was a Newton per, or rather a Newton per amp meter. Okay. And so what happens is the newtons cancel, the meters cancel, an amp is a coulomb per second, and so this comes out to be meters per second. Okay, so that is 1490 meters per second. Okay, when I was a student, I just had a huge fit with units. Okay, don't just write down the units you think it should be, because you're often wrong. Several people in the test had that problem. They just wrote down the units they thought it ought to be. They did the problem without doing any units, and they ended up getting the wrong answer. So now we know the speed. Well, once we know the speed, then this is cyclotron motion here. Okay, once it comes out of the velocity selector. And so the cyclotron radius is going to be given by mv over qb. So this is going to be, well, gosh, we need to know the mass of a sodium ion. Well, if you look up sodium, you find the mass is 22.989769 U. Well, that U is like an atomic mass type unit, and so that turns out is equal to the atomic mass unit here, the U, is equal to 1.661 times 10 to the minus 27 kilograms. So that means the mass of the sodium ion is going to be 3.819 times 10 to the minus 26 kilograms. It's ionized, so that means that Q is just going to be equal to E. Okay, so now we can find the radius here. The radius is going to be mv over qb. So that's going to be equal to the mass, and the mass was 3.819 times 10 to the minus 26 kilograms times the velocity, the 1490 meters per second. Q, 1.602 times 10 to the minus 19 coulombs. And then B is going to be equal to 0.0129 Tesla. So the R comes out to be 0.0275. Okay, so now we got to have our whole mess with units again. So we got kilogram, we have kilogram, so this is kilogram meter over coulomb second Tesla. Okay, and so back to the Tesla. What is the Tesla going to be? Well, we know that this is a kilogram meter coulomb second. We said that Tesla could be written as a kilogram per coulomb second. And so the kilograms cancel coulombs, so that's just meters. Okay. All right, so this comes out to be in meters. So 2.75 centimeters. Now, that's R. So D is twice that. So D will be 5.5 centimeters. All right, so that's where this thing lands. Think about the original situation here. We had crossed fields right here. We shoot something in here. It has a certain mass and a certain charge. As it goes through here, only one velocity makes it through, and then as it comes through, it comes over here and hits a detector. Okay, now, here comes the really interesting thing. Okay, The velocity that comes through doesn't really matter what the mass of the charge is. It only matters what those fields are. So that means no matter what we stick in here, it's going to only the ones that come out are going to be a certain velocity. The mass determines where it ends up over here, the mass and the charge. Okay, now we could actually have an unknown substance over here, which we just bombard with some neutral particles like argon or something, and it knocks things loose. We can zap it, ionize it, and then it's going to accelerate. And so that means we could use this if one mass comes in and lands here, something with another mass would land here, something with another mass lands there, something another mass lands up here. Okay, and so we could actually work backwards. So we solved this problem by giving you the mass, and you saw where it landed. We could have done the problem entirely backwards. I could have given you that D, and you worked backwards to find the mass. Okay, well, this turns out to be a very useful sort of tool. If you have a material, you don't know what makes up your material, you would simply use ions of that material, feed it into something like this, and then detectors would then read off the masses of the individual things that make it up. Well, we call such a device a mass spectrometer, and you would use this as a material characterization tool to find out what's in there. Now, you could do a mass spectrometer that's atomic mass spectrometer in which you do individual atoms, or you can have molecules, too. All you got to have is something ionized, either positive or negative. Negative ionized would actually go that way. And so a mass spectrometer would let you figure out the chemical composition of what you're looking at. And y'all have all seen these crime shows where they have some unknown substance and the lab tech sticks it in a little vial, sticks it in a machine, and says, oh, it's this. Well, this is the kind of machine that they're actually doing. Actually, the machine on TV show doesn't really do anything. It's probably just empty shell. But in real labs, they would have a mass spectrometer that would tell them what it's made out of.